Um, Welcome to the second presentation for today. I am Sreenidhi Krishnamoorthy and I am a PhD candidate in mechanical engineering. This is my fourth year of my PhD, and my project is on efficiency improvement of variable speed residential air conditioning system with ductwork. So the way I came to doing this project was I joined the Western Cooling Efficiency Center in 2014, and a year later my faculty advisor Mark talked to me about this project, and it seemed to be a good fit based on the work I did during the first year. And so this is a project sponsored by the California Energy Commission, and EPRI is actually subcontracting it to WCC. So the goals of this project are, the overall goal is to understand and determine the optimum operational settings of a variable capacity or variable fan speed air conditioner with ductwork in an unconditioned space. So the way I went about achieving that goal was first to obtain performance data for a range of summer conditions through full-scale laboratory testing. And during based on that data, I tried to balance the thermodynamic, aerodynamic, and heat transfer impacts of changing the compressor and fan speeds on the COP of the system. So I did that in order to find out the optimum points of operation, optimum compressor speeds and fan speeds to operate the air conditioner in. So once I had that information, I tried to understand how the optimum points vary when changing the amount and nature of load. By that I mean, for example, sensible versus latent climates, climates where more latent cooling is desired versus sensible cooling. I also did a zone optimization of the entire system. So I tried to use the ductwork as a multi-zone system and see whether that improves the COP. I also created a mathematical model to predict the equipment and distribution system efficiencies, and used that I validated that model using my experimental results, and then did some further analysis using that model to understand the design choice impacts, what will happen if the duct insulation increases, etc. So I was asked to prepare a presentation for 20 minutes, so I'm going to mainly talk about the experimental part of my work today. So before I do that, some reasons why this project was motivated. The first reason is, of course, the motivation to increase energy efficiency, because HVAC systems account for almost half of US home energy use, and basically that creates an additional burden on power plants. So energy savings is one of the important criteria. And talking of energy savings, the current technologies current research being done on energy efficient technologies, they focus on individual components rather than being evaluated for the whole system. So by that I mean, if you think of an HVAC system, there's the equipment, which an AC has a evaporator, the condenser, the compressor, and the TXV valve, etc. So there is research being done to understand how we can increase the efficiency of those components, and thereby increase the COP of the equipment. What I am trying to do is also try to factor in the efficiency of the distribution system, or understand how the situation where ductwork of the air conditioning system is in an unconditioned space, how that affects the efficiency of the overall system. Another reason why this is important is because current performance standards try to rate the HVAC equipment based on conditions like standard conditions which may not represent diverse climate zones. For example, as I mentioned, sensible versus latent cooling, or like a very hot and dry climate like the ones we have in California. The experiment, the way I went about doing the experiments was like we have, as many of you know, like we have outdoor and an indoor chamber in the WCC laboratory, and it's possible to control the temperatures and humidity and the airflow there. So I used a 2-ton split system heat pump for my testing. And I'll actually go to the experimental diagram to explain more. So what I did was I used the outdoor chamber, which is the bigger chamber shown here, to locate the outdoor unit, the indoor unit, and all the ductwork. So the ductwork is actually R6 ductwork, which means the insulation resistance is like 6 in IP units. And so there are 4 zones in this ductwork. The 4 lines actually show the 4 zones. They all split into further branches, which is not shown here for clarity, but they all end up in a wooden box where all the grills for a home are located. So basically the air is being delivered to the grills through 4 branches, which are not necessarily equal in dimensions. And the dimensions are like, you can see one duct is like 25 feet long, whereas another duct is 12 feet long. And they have different number of branches, and they carry different amounts of air. So, so that's a good representative duct to investigate how the distribution system efficiency is affected based on the variation of these parameters. So also, regarding the instrumentation, we measured the outdoor air temperature, which in this context is more the duct zone temperature. We measured the temperatures and pressures at the plenum and the refrigerant line, and we also measured the temperature of air leaving the grill and entering the ducts. And these are some pictures of how the ducts were assembled in the chamber. We tried to assemble the ducts on shelves, and the 4 blue buttons that you see there are representing the 4 zones. So we could activate or deactivate any of the zones by clicking those LED buttons. And then the other thing I wanted to mention was that the indoor unit is located in like way back in the chamber, and we had drain pans to eject the condensate. The top of this, which is not being seen, they contain the entrance to the 4 ducts. So that's the supply plenum there, that triangular metallic thing that you see there. I try to do 3 types of tests basically. Like one is, the first was like without zoning, with capacity and indoor airflow rate being synced. I tried to vary the capacity and indoor airflow together at 100% of the nominal capacity, 80%, 60, 40, and 25. Because 25 was the lowest capacity that the equipment was capable of obtaining. And I tried to vary the outdoor climate, chamber temperature from 29 degree to 46 degree in 5 to 6 degree increments. I actually control them in IP units, so like 85 degree Fahrenheit to 115 degree Fahrenheit in 10 degree F increments. And the indoor, I tested for 2 indoor conditions at 24 degree and 27 degree so basically trying to vary the the absolute humidity or a wet condition and a dry condition. And the analysis I did there was to understand the COP variations with outdoor air temperature, understanding the distribution system efficiency at different cooling capacities, understanding what are the optimum speeds of operation at different climates, and understanding the effect of sensible heat ratio on the performance of ducts. The second kind of test was to vary the airflow rate for a fixed capacity. So for each capacity that's shown here, I try to increase the airflow to 60%, 80%, and 100%. And I wanted to see what that does on the duct performance. And then I repeated the same two conditions for a multi-zone ductwork and try to understand what zoning does in regards to improving the efficiency of the ducts. So before I go to the results, I want to give a little bit of background on duct, a little bit more background on why ductwork was important in analyzing that. Most California ducts, homes have R6 ductwork, and they are located in unconditioned spaces, which so while the equipment performs really well at low speeds, the airflow rate through the ducts decrease at those low speeds, as a result of which the air takes longer time to reach the grills, by which the temperature, the heat gain in the ducts cause the temperatures to increase. So based on that, I tried to define 4 efficiencies. The first efficiency is just looking at the compressor only. So the COP of the compressor, which is the ratio of the cooling delivered by the evaporator to the power input to the condenser, where the cooling delivered doesn't include the fan power or the fan heat. And this is the kind of efficiency that we normally study in thermodynamics classes. But then the second type of efficiency is the equipment COP, which is trying to repeat the same as the compressor, but this time including the blower fan heat and the blower fan power consumption. The third one is the efficiency of the distribution system, which is defined as delivery effectiveness, or the ratio of the delivered cooling at the grills to the cooling provided by the equipment. And finally, the system COP, which is a combination of, you can think of it as a combination of equipment COP and delivery effectiveness, the product of those two. So the ratio of cooling delivered at the grills to the total power input to the equipment. So the first, I'll show results for each type of tests I did. First is when the capacity and airflow rate was synced and there was no zoning. So the graph on the left side is delivery effectiveness versus capacity and airflow at 4 different outdoor temperatures or duct zone temperatures. So you can see that as the duct zone temperature increases from the green line to the blue line, the delivery effectiveness drops sharply, and that's understandable because the heat gain in the ducts increase. But the delivery effectiveness also decreases as we decrease the capacity and airflow rate. It decreases with airflow rate because of the reason that there is longer residence time in the ducts, and it decreases with lower capacity because even though we reduce capacity, the duct losses do not go down in the same proportion. They are not reduced significantly because we are keeping capacity and airflow rates synced, and as a result the duct inlet temperatures don't change. And as a result of that, even though the equipment COP actually goes up with reduction in capacity and airflow rates, which is the reason why variable speed systems are important, the system COP actually has some optimum points of operation. For the green line, the maximum system COP occurs at 60% capacity and airflow. That's at a low outdoor air temperature. For the middle two lines, yellow and orange, red and orange, the optimum occurs at 80%. And then as we go to even hotter duct zone temperatures, the optimum is more like 100%. So reducing capacity or airflow is actually not beneficial in that case. Another thing I want to show you is that the duct effectiveness is not as, it's a non-trivial effect. Like if you see the 40% line at, for the blue line, the 40% point, the equipment COP may be like 3 in that, for that point, but because the delivery effectiveness is like 40%, the system COP it drops down to like 1, around 1. Okay, yeah, so these are the main points here. So basically the optimum speed setting increases as we increase the outdoor air temperature. The next set of results in this category is trying to do the same capacity and airflow variation synced tests, but at different indoor conditions. So the blue line is actually a dry climate, dry indoor condition, whereas the red line is a wet, the 80-67 condition. So you can see that the system COP actually increases for the wet case. And there are two reasons for this. One is obviously the equipment COP is higher, but in terms of the ducts, there is increased delivery effectiveness at lower percentage of sensible cooling. Duct heat losses or thermal losses in ducts are primarily sensible, and in wet conditions, the amount of sensible cooling is lower, so that increases the delivery effectiveness. Now I want to show you the results of varying the airflow rate for a given capacity. So what you are seeing here is compressor COP as we vary the airflow rate at different capacities. And you can see that they are pretty good, like around 6 to 7 for the low capacities. And then you can also see that the compressor COP increases as you increase the airflow rate. And there are two reasons for that. One is as you increase the airflow rate, the heat transfer coefficient goes up. And secondly, the air is not able to reject as much heat as it could have at lower airflow rate. So because of that, the refrigerant temperature leaving the evaporator is higher, and so the refrigerant sees a lower delta T, and that increases the thermodynamic efficiency. But as we go to the equipment COP, which now includes the fan power and fan heat, the values come down, and like it kind of negates some of the advantages of the thermodynamic efficiency. And finally, when you include the heat transfer impacts, so the distribution system, when you include that and look at the system COP, you can see that the curves, the points are basically flat, like the system COP is like almost insensitive to changes in airflow rate. And you can also see that the values are much lower, like those were around 6 to 7 have now come down to 3 or 4. So the point is that the increased fan power and duct losses together tend to cancel out the efficiency gains in the compressor. And then now looking at zoned operation. So clearly the problem of distribution efficiency, distribution losses need to be addressed. And there are a few ways that we could do that. One is to increase the insulation level of the ductwork. So R6 can be increased to R8. That's one possibility. Another possibility is to locate the ductwork in a conditioned space so that the amount of heat losses, heat gain in the ducts actually go down. A third way, which is relatively simpler, is to add zone dampers at the supply plenum and create a multi-zone ductwork. The reason why this is efficient is because if, let's say, we are reducing the capacity from 100% down to 40%, we can pass that capacity through only 40% of the ductwork rather than the whole ductwork. So maybe one zone carrying 40% or two zones carrying 60%, which means roughly one zone carrying 30%, rather than 100% of the ductwork. So what you are seeing here is that the delivery effectiveness decreases when all the ducts are carrying some capacity. But when some zones carry some capacity, so in proportion, the delivery effectiveness actually goes up because of the airflow rate, the residence time doesn't change that much. The only losses that remain fixed are the return duct conduction losses. And actually this, although we tried to make the four zones here roughly carry 20 to 30% capacity. So it's not exact that one zone carries 25%. So you can see that actually for this setup the delivery effectiveness goes up. And then now looking at system COP, this actually tries to summarize the different tests I've done in different operating modes. The gray bars are running the system at 100% capacity and 100% airflow rate at different outdoor temperatures. The orange is trying to reduce the capacity and airflow rate like down to 60 or 80. So trying to see what variable speed systems do to the efficiency. And the blue line, the blue bars, which you can see are the highest in all cases, are adding the zoning, the multi-zone ductwork. So the COP increases when you reduce capacity and airflow for variable capacity systems from gray to orange, except that as you go to higher temperatures, the impact becomes lower and lower. But if you also include a multi-zone ductwork, the COP is the highest. And so what that means is that zoning is one of the solutions to address the distribution system efficiency. And another point is that if you one result that I've not shown here is trying to do a 40% capacity at the high outdoor air temperature condition with a zone ductwork. So what I noted was that the gray bar is almost equal in value to a situation where 40% capacity is run through one zone, which is which addresses the problem of demand response. So during a demand response event, a variable capacity system without zoning would actually prove negative to the efficiency. But if you include a zoned system with that can allow further reduction of capacity or airflow through demand response. So basically, to summarize, duct losses play a significant part, and the system balance changes with duct zone temperature, and that can be solved by a zoning system. And then COP of a variable speed equipment can be increased through zoning. I'd like to ask questions, but before that I thought it might be interesting to show you some personal lessons that I learned from during the last 3 years. One is that experimental details that seem to be minor are not necessarily too minor. And an example is during the when I assembled all the ductwork in the outdoor chamber, I thought that I've done everything perfectly and there should be no leakage. But when I did a leak test, I saw that almost 10% of the air is actually leaking. So I had to fix all that, and then also working with a schedule was really important. And then working on projects like this helped me really to get into a research mindset and think of new ideas. So, thank you.
So, it's one of your takeaways that more than two zones doesn't get you better payoff, that just two zones is optimal?
Yeah, so, actually when we go to, one of the drawbacks of going to lower number of zones is increasing the fan power, because we increase the pressure drop through pressure rise through the fan, and that actually creates a drawback. Yeah, so for the experiments I only considered conductive heat loss, but in the model I also tried to, I have an input where I can consider leakage losses.
Out that addicts, or maybe you did, did you point out that addicts actually run a lot harder?
I haven't. Yeah.
So basically all of those analyses that you showed will actually get worse, sometimes significantly worse. And Janelle pointed out that in addition to that, the roof is going to be even hotter than the air temperature, and so the radius gains going to be non-trivial. So the end result is it looks even worse than anything you showed.
I haven't considered that. Okay.
Probably do is turning it into an operating. So basically, I mean, you could do a whole fancy analysis of radiant transfer, but probably you could just take the attic roof temperature, feasible down to that, and turn it into an operating. Just to make it simple. At a certain point, the message doesn't change, right? It doesn't change the direction. Actually, the controller can be a lot simpler. It's not going to change your optimum very much. It's a little bit of optimization simply by saying the first order, just whenever you run at a lower percentage than 100%, run that same percentage of the ductwork, no matter what. The next level of sophistication, rather than trying to figure out a model, attic, and all that kind of stuff, just measure the temperature's coming out of the grill. If you know the temperature's coming out of the grill, then you can adjust this. So that would be a much simpler way of doing it. Well, you notice
Yeah, I have. So I have, so actually the next phase of this project is to do field testing where we are doing one site with an R6, another site with R8, and third site was going to be R10, but they have now chosen R8 for that zone. So what I've seen is that there is an improvement in the obviously there's an improvement in the delivery effectiveness, but I think that the improvement in due to zoning is definitely higher than improvement without zoning with an increased insulation resistance.
So you said the improvement with zoning is greater than the
Yeah.
improvement of adding insulation to the
Yeah,
house.
yeah.
Interesting. Can the chamber go to a very high? And you get to a temperature that's higher than the 46?
Well, the test we've run are like 1.5. The problem is the condensers.
There's always going to be a differential. There's going to be no differential between.
Your outdoor and your attic temperature have to be the same.
You build us another chamber.
Let's do it this weekend.